Kia ora and welcome to question 2 of the 2009 School Calc exam. Again, 3 parts to this question. The first one, another trig identity kind of proof. 2b, something to do with volumes of revolution. And 2c, a proof involving Simpson's rule, which is a numerical method taught in NCEA integration. Usually appears as an achieved question, so quite uncommon for something like that to feature in School Calc. Alrighty, 2a, we've got this hyperbolic cosine function, which is defined as a sum of exponentials divided by 2. Okay, so you're not expected to know that without its definition. And we need to prove that if we replace the x's with 3x's, so the hyperbolic cosine of 3x is equal to 4 times itself cubed minus 3 times itself. Okay, so starting probably on the right hand side, because there's a little bit more to do. I can just straight dump this thing into the right hand side without having to play around with exponentials. Okay, so right hand side equals the hyperbolic cosine cubed with a 4 in the front. Okay, 4 times this dude cubed minus 3 lots of the same thing. Okay, we need to cube that expression, so I'm going to use the binomial theorem for that. First of all, I'll pull the 2 cubed out of the denominator as an 8, so we've got 4 over 8. And then e to the x plus e to the minus x all cubed. So the first thing cubed plus 3 lots of the first thing squared times the second plus 3 lots of the first thing multiplied by, don't need brackets for that, what am I doing? First thing multiplied by the second thing squared plus the second thing cubed. Okay, and then we're minusing 3 over 2 times e to the x plus e to the minus x. Okay, now I showed the long form for the binomial expansion, but you might have realised that this part here, e to the x all cubed, is just e to the 3x. So you might have shortcut that step. 4 over 8 is a half. So we've got e to the 3x. The next term in, this one here, we've got e to the 2x times e to the minus x, and we add the powers, we get e to the x. So I've got 3e to the x there. The next one I've got 3e to the minus x. And then the last one, e to the minus 3x. Minus 3 over 2 times e to the x plus e to the minus x. Okay, now the terms we're expecting to cancel actually do. So 3e to the x divided by 2 cancels with that one. And 3e to the minus x divided by 2 cancels with that one. And we're left with e to the 3x. Oops. E to the 3x plus e to the minus 3x all over 2, which is of course the hyperbolic cosine function where 3x is the argument and not x. So it equals left hand side. Happy days. Not too bad. Okay, part B. P and A are constants greater than 0. We've got a curve y equals x to the p. Between 0 to the 0 and a to the p is rotated once around the x-axis and once around the y-axis to make 2 separate volumes of revolution. What values of a in terms of p make the 2 separate solids of equal volume? Okay, so this was set in an exam where they didn't give you the volume of revolution formula because it used to be part of the integration achievement standard and it was on the formula sheet. So I suspect that if it was given to you in an exam nowadays, you'd get the formula to start you off. So I'll do that for you. You might want to pause the video and see if you can remember it yourself. And I'm also going to consider P to be 2, just so that I can think of the curve as a parabola. And I don't know, A to be 2 as well. Doesn't really matter. But I just want to draw that picture. Okay, so we've got y is equal to x to the p. So let's go and just draw that, like I said, for a parabola. And we're drawing it between the origin and some point x equals a. And then that value there was a to the p. Okay, so if I rotate that around the y-axis, the whole curve around the y-axis, we're going to get like a bowl kind of shape. Should be flat at the bottom. And to do that, I've got pi times the integral of x squared dy between y equals 0 and y equals a to the p. The pi x squared bit comes from the fact that if we take a cross section of this volume, it's circular and the radius there is x. So the circle has an area of pi x squared and the thickness of each slice is dy. Okay, if I rotate it around the other axis, get some sort of like horn, trumpety kind of shape. The only thing that changes in the formula is the variables get switched around. So I'm integrating between 0 and a this time, and it's y squared dx. Okay, we want these volumes to be the same. Okay, so the first one, pi times the integral of x squared. Well, that's where we need to rearrange the top equation. Y equals x to the p is the same as x equals y to the 1 over p. We take a power of 1 over p on both sides, and therefore x squared, which is not related to the fact I've drawn a parabola or anything. The parabola is just there to get the idea of the shape, but we need the squared because it's r squared in the area formula for a circle. So it's going to be y to the 2 over p. So that's what we're integrating. Remember that p is just a constant. dy between 0 and a to the p. Increase the power by 1. Divide by the new power. All between a to the p and 0. Pi. The pi's will cancel because there's one on both of the volumes and we're making these volumes equal. Okay, the right hand side one, pi y squared dx. So we just take the original expression for y, which is equal to x to the p, power it by 2, so x to the 2p. X to the 2p plus 1 divided by 2p plus 1, a and 0, make those, oh, there's a pi, make those equal to one another, cancel the pi's off, and sub in these limits. So we've got a to the p all to the power of 2 over p plus 1 divided by 2 over p plus 1 equals a to the 2p plus 1 all over 2p plus 1. Bearing in mind that when you sub in the 0 values into the definite integral, you get 0. They're both in the base. Now, the question asks us to find a in terms of p. So we're solving an equation here that's got powers in it. The first thing is I'll tidy up the power at the top left by multiplication. Okay, multiplying that p times 2 over p is just 2, and p times 1 is p. I can also tidy up the fraction at the bottom. 2 over p plus 1 is the same as 2 plus p all over p by adding fractions. cross multiply the thing. I want the a's on one side and I want the other stuff on the other side. So 2p plus 1 goes from the bottom right to the top left. All over 2 plus p all over p. Make sure that when you're dividing fractions that you leave the middle fraction bar bigger than the fraction bar at the bottom. And then that's a to the 2p plus 1 all over a to the 2 plus p by taking the top left thing, moving it down the bottom right. The fractions on the left can be divided. When you divide a fraction, you times by the reciprocal. So we get p times 2p plus 1 all over 2 plus p. And the right hand side thing, same base of a, which means we can subtract the powers. A to the power of p minus 1. And lastly, we're needing to make a the subject of this, so we power this whole thing by 1 over p minus 1. 2p squared plus p all over 2 plus p to the power of 1 over p minus 1. And does that quadratic divide the linear factor? No. So we'll leave it at that. Okay, part C. Show that Simpson's rule using n equals 2, so that's 2 subintervals. Just a reminder of kind of what Simpson's rule does. So if we have some sort of function, f of x, and we want to find some integral, which often is an area-based question, but not always. If we want to integrate it from some value xa to some value xb, we can divide this region up. It's called a partition, and then we can approximate the function. Sometimes, in the case of a trapezium rule, you approximate it by trapeziums, so you approximate the function. So another trapezium there, and so on. And the tops of the trapeziums, you can approximate them as linear functions. So that's Simpson's rule is along the same track to that. On the formula sheet, you're given the formula for Simpson's rule. The integral between a and b of f of x is approximately h over 3. And I can never remember it, which one's even, which one's odd. And by the way, the h is the horizontal step size, so the width of the trapeziums in that diagram, or just how many shapes you break up the total region into will define how wide the h value is. Just reading straight off the NCA formula sheet, we've got y0 plus yn plus 4 lots of the odd ones plus 2 lots of the even ones. So that's odd, that's even. Okay, and we're apparently going to get an exact answer if we integrate a quadratic between r and t. Okay, so let's show that. First up, let's integrate the quadratic. Ax squared plus bx plus c between r and t and see what the exact answer is. So we can use integration to do that. These methods are used when you can't do the integration because in some cases functions don't have antiderivatives or they're too difficult to find. Okay, so substitute the t value in. At cubed over 3, and then we're going to eventually get a minus ar cubed over 3, so I'm just going to do that in one go. So we've got t cubed minus r cubed. We've got b over 2, we sub in the t value first, t squared minus the bottom value second, and then lastly c times t minus r. So that's the exact value of this integral. Of course, in most questions we know what a, b and c are because we know the specific parabola and we know what the limits are, so we just get a number. This is a number, it looks like a horrible expression. Okay, so Simpson's rule. We're taking our function and we're dividing it into two intervals, and we're going between r and t, So let's call, or we could call this middle one here S, potentially why they've used letters of the alphabet with one letter missing in between them. And we just need the y values. That's what the beauty of these numerical methods. We don't need integration, we just need the y values of those things. So that's the y value of R, the y value of S, and the y value of T. Okay, so H over 3. Bear in mind we're just finding this part here. So looking back at that formula that I had, we've got this thing in the front which is H over 3. In our case we're going from R to T, so the total width is T minus R. We're going to divide it by 2 because we've got 2 regions, and then we also divide by 3. So T minus R all divided by 6 times the y value at the end, which is the y value of R, just call it y subscript R. Also the y value at the other end, yt, and then the one in the middle is an odd one, because this is like y0, y1, y2. So y1, the odd one, we get multiply that by 4. 4 lots of ys. Just to check I've actually had that formula correct. Yeah. Here we've got the end points, y0 and yn, plus 4 lots of the odd, 2 lots of the even. We're only breaking it into 2 intervals though, so we don't get any even ones. Okay, now we use the parabola equation to find those y values. The y value of R is just a r squared plus br plus c. Y value of t, at squared plus bt plus c. And 4 lots of the y value of s. Now, there were no s's in our expression for the exact integral, which means that we shouldn't put s into this one. S is the average of r and t. S equals r plus 2 all over, r plus t all over 2. So we've got 4 lots of, this is where it gets really messy. A x squared, so a times r plus t all over 2 all squared, plus b r plus t over 2 plus c. Somehow we've got to prove that it comes out to be the expression at the top of the page. I guess you could just expand the whole thing out and see what you get. Probably the quickest way to do it, to be honest. So let's go looking for some like terms. Okay, we've got ar squared there. Have we got any more r squareds? Here we do. In the last bracket we've got an r squared in there. It's r squared over 4. It's also times by 4. So that loses the fraction. We've got an a in the front. So it's 2ar squared. Probably the same with the t squareds. We've got a t squared term there. We've got another t squared term in there. It's t squared over 4 times by 4 is at squared. Yep, so 2at squared. And then the linear terms. Let's look at, so BR term. There's another one there, BR term there, which is a half, but it's times by 4. So it's 2BR, so it's 3BR in total. And in terms of the BT term, it's the same. And then the constant terms of C, there's 2, running out of highlighter colours. There's a C there and a C there. I'll be already dealt with the BT term. 2 C's and another one right at the end, but it's times by 4. So 4, 5, 6 C. And lastly, there's an RT term, which is inside the squared. When you expand the r plus t over 2 all squared term, you get 2RT, but it's divided by 4, and then it's times by 4, so it's 2RT times A, so we get 2ART. Oh, how great thou art. Alrighty, now we need to consider the t minus r all over 6 thing at the front. We can deal with the over 6 thing because we've got 2 over 6 for some of the terms, 3 over 6 for some of the terms, and 6 over 6. So let's go t minus r times ar squared plus at squared all over 3 plus br plus bt all over 2 plus c plus art all over 3. Okay, does it look anything like this? Do we have an ART term in that? Oh, we must do in the first cubic part. Okay, rather than try and factor this, which is what I was considering initially, because it has got a factor of, oh no, that actually would have been clever. Oh, why didn't I do that? I'm trying to expand it to get to that, but this is actually quite easy to factor. Why don't we just do that? A over 3, t cubed minus r cubed has a factor of t minus r, because t equals r is a solution, it makes it go to 0. And then it's going to be t squared plus rt plus r squared. Okay, you can check that that is what t cubed minus r cubed, a difference of 2 cubes, factors to. And then the second one is a difference of 2 squares, t minus r, t plus r. And then the last one's got the t minus r. So if we pull a t minus r factor out of that, we've got a over 3 times t squared plus rt plus r squared, b over 2 term times t plus r, and a c. Alrighty, I'm just going to be lazy here and just take that all the way down to the bottom. And just see if it's the same. I've got an AR squared over 3, yes. We've got an AT squared over 3. We've got an ART over 3. B over 2T, B over 2RC. Perfect. All equal. And I'm just going to leave it there as a proof, even though it was a little bit dodgy. In the exam, you would either work it through by expanding it and then showing it equal to the thing we had, or you would go with the factorising method, and I've kind of met in the middle a little bit, but hey, I can finish the video now.